Aging is not a single process, but a symphony of biological changes unfolding across the molecular, cellular, and systemic levels. For decades, scientists studied aging by examining isolated markers, cholesterol levels, telomere length, blood pressure. But this reductionist approach could only offer fragments of insight. Today, aging research is undergoing a revolution thanks to multiomics, the integration of genomics, epigenomics, transcriptomics, proteomics, metabolomics, and more. Together, these layers form a detailed molecular map of how the body changes with age, and what distinguishes long-lived individuals who remain healthy from those who develop age-related diseases. Nowhere is this comprehensive view more evident than in pioneering studies like Cilento, the Comprehensive Assessment of Aging Outcomes, an ambitious European initiative focused on understanding why some people age with vitality while others experience decline. The CGO study and others like it aim to chart a 360-degree view of human aging, combining multiple omics technologies to identify patterns, drivers, and possible interventions for extending health span, the number of years a person lives free of serious illness or disability. At the foundation of this effort is genomics, the study of an individual's DNA blueprint. While it's true that genes influence how long and how well we live, they set only the stage. Environment, behavior, and time shape the performance. Genomics identifies inherited risk factors for diseases such as Alzheimer's or cardiovascular disease, but by itself, it cannot explain why two people with the same genetic risk age differently. That's where epigenomics steps in. Epigenomics explores how gene expression is turned on or off through mechanisms like DNA methylation and histone modification. This dynamic layer reflects the body's responses to diet, stress, pollution, sleep, and other lifestyle factors, and is crucial in determining biological age, a more accurate measure than the number of candles on a birthday cake. In fact, one of the most powerful tools in aging research today is the epigenetic clock, which uses methylation patterns to estimate how fast a person is aging at the cellular level. Complementing these is transcriptomics, which looks at RNA expression, the actual messages sent out from DNA to produce proteins. RNA profiles shift as we age, often in response to inflammation, oxidative stress, or cellular senescence. By tracking these shifts, researchers can detect early signs of immune system decline or tissue dysfunction, sometimes decades before disease becomes apparent. Next comes proteomics, the study of all proteins produced in the body. Proteins are the workhorses of biology, enzymes signaling molecules, structural elements, and they reflect both genetic instruction and environmental influence. In aging research, proteomics is used to track markers of inflammation like IL-6 or TNF-alpha, mitochondrial function, DNA repair, and immune response. Changes in the proteome can indicate early signs of neurodegeneration, metabolic disorders, or cardiovascular stress, making it an invaluable tool for detecting the subtle onset of dysfunction in systems that otherwise appear clinically normal. Then there is metabolomics, which profiles the small molecules involved in metabolism, such as glucose, amino acids, lipids, and antioxidants. These molecules offer a snapshot of real-time physiological status, what the body is doing right now. In aging studies, metabolomics helps track insulin sensitivity, oxidative stress, mitochondrial efficiency, and nutrient processing, all of which change with age. One major insight from CAO and similar efforts is that long-lived individuals often have metabolomic signatures associated with efficient energy use, low systemic inflammation, and stable glucose and lipid metabolism. This real-time data helps researchers identify modifiable pathways for intervention through diet, exercise, or pharmacological agents. Importantly, these omics layers don't operate in silos. They interact. A genetic predisposition may be amplified or silenced by epigenetic marks, which influence what RNA is transcribed, which proteins are produced, and how metabolism adapts. Multiomics approaches allow researchers to see these complex, interwoven pathways in action. For example, a person with a gene variant associated with inflammation might not show elevated risk unless certain epigenetic patterns and metabolomic profiles also emerge, providing a far more nuanced view than any single test could offer. Studies like CIO also focus on phenotypic anchors, physical performance, cognitive testing, cardiovascular markers, and mental well-being scores that connect molecular data to real-world aging outcomes. By integrating omics data with these functional outcomes, researchers can start building predictive models of health span, tools that not only forecast disease risk, but help guide personalized interventions to delay or prevent its onset. One of the ultimate goals of this research is to identify actionable biomarkers, molecular signatures that don't just correlate with aging, but can be modified through lifestyle, therapeutics, or environmental changes. Already, insights from multi-omic studies are informing efforts in precision nutrition, exercise physiology, and regenerative medicine. They also offer hope for identifying early signs of frailty, cognitive decline, or immune dysfunction years before symptoms appear, opening a window for true preventive healthcare. In the end, multi-omics is transforming our understanding of aging from a linear, universal process to a deeply individualized and modifiable journey. By mapping how genes, proteins, and metabolites respond to life's challenges and choices, scientists are uncovering the complex choreography that defines healthy longevity. This approach doesn't just promise longer lives, it offers a framework for living better at every age, with more energy, sharper minds, and a greater capacity to adapt to life's changing rhythms.